Okay, this will be the lecture for Chapter 23, Electrical Current, or really kind of what we're talking about is how we can form circuits. So I'm going to talk about what a circuit does. A circuit's going to let charge flow from one place to another. We're actually going to call that current. And how do we make it flow? Well, we are going to need a power source or a voltage source, and we're also going to need somewhere for it to go. We're going to need a load or someplace where there's some resistance. Ohm's law is going to marry all three of these. Is going to talk about the voltage, how it's related to the current, as well as the resistance. And I'll talk a little bit about direct current circuits and alternating circuit currents, what happens with the electrons inside of a circuit, a little bit about electrical power, and how electrical power is related to light bulbs, CFLs, or LEDs. And then I'll talk about two types of electrical circuits. I'll talk about how we can wire things up in series, or how we can wire things up in parallel, and kind of the difference between the two of these guys. It looks like a lot of information, but it's a little bit shorter than last chapter. So any circuit that we have, it's going to have something that's really important. It's going to have an electron pump, essentially, and this is going to be a battery. And what it's going to do is it's going to take some electrons from the positive end, and through some chemical means, it's going to convert some of that chemical potential energy into some electrical potential energy. So it's going to do some work. It's going to take those electrons and going to move them down right here. What we're going to end up with is we're going to end up with a bunch of negatives down here and a bunch of positives up here. And what's going to happen is we're going to have some electrical field present, and surprise, surprise, if we were to put a charged particle inside of this electrical field, then it's going to move. It's going to feel a force in that direction, in the direction of the electrical field. Generators actually do the same thing. They're essentially a fancy electron pump, if you will. Now, what goes on inside of a battery? Again, this is going to be a chemical process, and I'm not really a chemist, so I'm not going to hold you to too much of this, but let's just talk about a lead-acid battery. They're one of the more common ones. A lead-acid battery is going to have a lead anode. Anode is fancy for negative terminal, and it's going to have a silver cathode. Cathode is fancy for positive terminal, and these guys are going to be submerged in this case, some sulfuric acid, and we're going to have two reactions occur. We're going to have some lead and some sulfate, make some lead sulfate and two free electrons. The electrons are negative, hence the negative sign right here. And on the positive side, we're actually going to get two hydrogens and two electrons are going to form some hydrogen gas. It's taking away two electrons, hence the positive. And bear in mind that you do have to outgas these lead acid batteries. So anyway, and through some chemical means, we're separating out some charge. A couple of things to bear in mind when it comes to batteries is if you stack them together, then their voltages are going to add. So if you took two batteries like this one is 1.5 volts and this one is 1.5 volts, and if you were to put a voltmeter across right here, there's a really good chance that we're going to measure 3 volts. So voltages can essentially straight up add together. Now, you may ask yourself the question, well, what if I had some batteries and I stacked them up in some weird configuration, so 1.5 volts, 1.5 volts, and 1.5 volts? Well, from here to here, I'm going to gain 1.5 volts. From here to here, I'm going to lose 1.5 volts. It's in there, so technically it's going to be negative. And then from here to here, I'm going to gain 1.5 volts. So if I measured my voltmeter across from right up there to right up there, I'm really only going to measure 1.5 volts, and that's going to come from this battery right here. Doesn't make a whole lot of sense to do this, but I'm just kind of saying that voltages can kind of add. Now, I always kind of like to think of batteries as being climbing the stairs to something. And if I were to, climb the stairs up the world's tallest roller coaster, then essentially what I'm doing is I'm stacking up a bunch of batteries. The higher I stack these batteries up, then the higher the voltage that I'm going to have. So in some ways, voltage is going to be a whole lot like the gravitational potential that we're going to have. What's going up the stairs? Well, people, or in the case of batteries, then electrons. Once we've raised some electrons up to some voltage, then these electrons can slide down the world's tallest water slide, which is this guy right here, and they can flow. We have a special name for this flow of electrons. We're going to call the flow of electrons current, and what drives the current? Well, it's going to be voltage. Now, current is going to have a special symbol. It's going to be a capital I. Anytime I write the capital I, I'm talking about current. And the unit for current is going to be the ampere, which has a capital A. Now, what we can kind of think of is we kind of think of positive charges flowing down a river, and it's going to be the flow of these positive charges that's going to be the current. So one thing to bear in mind is if I were to have some positive charges flowing in this direction right here, then I'm going to say, well, I'm going to have my current flowing in this direction. Now, you may be saying to yourself, wait a minute, you've said up until now that it's the electrons that are doing the flowing, and technically we are correct. Electrons do the flowing, but there's something called conventional current, and then there's kind of a real current. A real current is going to be the direction that the electrons move. And if I had electrons flowing in this direction, then that's kind of like having positive charges flowing in this direction. So bear in mind that I always talk about the flow of positive charge, but really it's going to be the electrons that really do the moving. The person to blame for this is going to be this guy right here, Benjamin Franklin. He actually said that we have positive and negative, but he kind of messed up what was positive and what was negative. So in reality, we can talk about how current is going to be the direction of flow for positive charges, but just bear in mind, in the back of your head, it's the electrons that actually do the moving. Now, the final piece to our puzzle is we know that voltage is going to go ahead and lift some electrons up, if you will. And then the flow of electrons is going to be what we call current. And then we ask ourselves, well, what if there are rocks? What if there's something to impede the flow of that current? Or if we were to talk about some positive charges flowing down the river, what if there's some rocks right here? Well, there's going to be some resistance. And resistance is going to be friction that impedes the flow of current through that circuit, just like rocks do inside of a river. Cue the light bulb. The light bulb is actually going to be what we would call a resistor. And what it's going to do is it's going to slow down the electrons, and it's going to heat up, and it's actually going to start to glow. So it's barely going to let the electrons flow through it, and it's actually going to consume a lot of that electrical potential energy. It's going to heat up, and it's going to produce thermal energy, and if you get enough thermal energy, then it's actually going to produce lights. So it's going to be a resistor. It's going to resist the flow of electrons through it, or positive charge, if you will. And the unit for resistance is going to be an ohm, and the ohm has a symbol that looks like this. It's a capital omega, and the symbol for it is going to look like that. Again, the unit kind of tells you what you're looking at. If I've given you 10 volts, we know we're talking about a potential. I've given you 10 amps, we know we're talking about a current. 10 ohms, we're talking about a resistance. So now we can kind of put all these guys together. We can put our light bulbs, we can put our batteries, we can use some wires to let the current actually do the flowing, and we can give it a load. We can give it somewhere for that potential energy to go, hence a flashlight. Now, the one thing we have to bear in mind is the current does need a path, and it does need a complete path, and it needs to go from the positive side to the negative side. So ask yourself, does this guy work? Well, this is the positive side, this is the negative side. I don't know about you, but I don't see anything connected to the negative side, so I don't see a complete path. So this probably wouldn't work. Now, take a look at this guy right here. We've got the positive side, we've got the negative side. This actually still wouldn't work because we're really still only connected to the positive side of the battery. We need something to connect to the negative side. We need a complete path for that current to flow. Now take a look at this guy right here. Here we have the positive side, here we have the negative side. And I'm just going to say the positives flow for a second. They're going to flow right here. They're going to flow through the resistor. They're going to flow out here, and they're going to flow down here. Now we have a complete path. So would this one actually work? Yes, this one would actually work. So again, let's come back and put all of these guys together and talk about a flashlight. We're going to have a battery that's going to be the energy source, converting chemical to electrical potential. We need a wire somewhere for the electrons to do the flowing, probably made out of metal, like, copper. We need a destination, we need a light bulb or a resistor. we actually need a switch. The switch is going to allow us to open and close the circuit. If you want the light bulb to be turned off, then you leave the switch closed. If you want the flashlight to turn on, then you close the switch, make some good contact right here, and then the switch is going to be closed and current can flow. No current is going to flow unless these things are connected, and we have a special name for that. We're going to have an open circuit. Now, symbolically, we kind of draw the battery to look like this inside of a circuit, and for reasons that are unbeknown to me, the long side is always positive, the short side is always the negative. Wires tend to look like this, batteries are going to tend to look like this, and resistors are going to be this little squiggly guy right over there. And if we were to look at this circuit right here, in a schematic sense, it's going to look like this guy right over here. Kind of move the switch off to the side, but we don't really draw the switch too awful much. The direction of flow is going to be the direction that positive charges would take, and they would flow off of this positive one. They would flow through the resistor, and they would come to the negative sides. We have our complete path. Bear in mind it is the electrons that do the flowing, but I always kind of say, where would the positive guys actually flow? Now we can go ahead and put all of these things together through Ohm's law. And Ohm's law is pretty straightforward. It's going to relate the voltage to the current and the resistance, and it's pretty straightforward. The voltage is going to be the product of the current times the resistance. The direction of current flow would be this direction right there. Again, the direction that positive charges would flow through the circuit, and kind of let there be light. Let's just do a quick little calculation. Suppose I had a 5 ohm resistor and a 10 volt battery source. How much current is going to be flowing through this current circuit? So how much of this guy right over there? Well, the current is going to be the voltage divided by the resistance, and all I've done is I've divided this by resistance and this by resistance to isolate this guy right over here. So I'm going to have my 10 volts divided by my 5 ohms, and I would say that we have 2 amps flowing through that circuit, which is quite a bit of current actually. Now, you may ask yourself, well, what happens if I took the batteries out of a flashlight and I put them in backwards? Would it still work? And the answer to your question would be, in a physics sense, yes, in theory it would completely work. If I had a battery like this, then I would say the current's flowing in this direction. I flip that battery around, so here I've flipped it around. The current would still flow. It would still flow through the resistor. It would just flow in the opposite direction. Now, bear in mind, this is a very simple flashlight, and more complex flashlights or things like cell phones, they have some circuitry where current can't flow backwards through some of the stuff. But in the simple-most circuit, yes, it absolutely can. Now, what happens if you have a flashlight and you've been running it for a long time? Then it's going to tend to dim, right? Probably not telling you anything that you don't already know. Well, what happens to a battery as it gets old? Well, if a battery initially has 1.5 volts, as it kind of goes down through chemical processes, then this might drop down to 1.45 volts or 1.4 volts or so on and so forth. We're not really going to change the light bulb here, not technically, and so essentially as the voltage goes down, the current inside of a flashlight might go down, and as the current goes down, then less of that power is converted into thermal, and we're going to have a flashlight that is slightly more dim. Now, one kind of implication of Ohm's law is going to be voltage is current times resistance. And we could have high voltage and high current if the resistance was relatively low, but we could have high voltage with low current if the resistance was relatively high. And you may be slightly afraid of high voltage power lines, and you probably should be, but bear in mind that it's actually electrical current that is what gets you. It's actually not voltage, because we have resistance to factor into account here. So a current of 0.01 can be felt. 5 milliamps can be quite painful. Your muscles start to spasm around 0.01 amps, and you lose control about 0.015. And if it gone through the heart, then 0.07 amps can actually kill you if it lasts for long enough. Again, it's really not the potential difference that is going to matter. It's going to be the electrical resistance of the body that's going to dictate the current that flows through you. Now, I'll kind of finish off this chapter by answering the age-old question: why do we have 3 plugs inside of higher draw devices like microwaves and dryers and stuff like that? Well, if we were to talk about wall voltage is always 120 volts. And what's going to happen is we're going to have current flowing like that through some device and flowing like this back into the wall, hopefully. This device has some resistance, it's got some load, and in theory you can touch the top of that device and everything is perfectly happy and hunky-dory. But what if something shorts out inside of that device? What if for some reason the load doesn't go to the wire? What if it goes to the case? Well, in that case right there, well, that's going to shock you, and that's not going to be pleasant. And the current's not going to flow through the intended load. It's actually going to flow through the ground, back into the wall, back somewhere like that, and that would probably be a bad thing. Now, what that third plug actually does is it grounds this device out. So it takes the case, and it runs it back to the wall socket, it runs it back to that ground, and it's going to take it somewhere safe. So that way, in the event that this does happen, then you're relatively happy. You might have noticed that this ground plug is always longer than the other ones, and that's just in case you're already touching this thing when you plug it in. So that way the very first this thing does is it goes to ground.